All right, we're going to start to talk about the history of the Earth. So chapter 11 in the textbook goes through the different kinds of conditions that have occurred on the Earth's history throughout time. And so now that we have a lot more understanding about geology and these different processes, we're going to start from the beginning of the Earth's history, which is also where we started at the very beginning of the semester, but we're going to go through and talk about these different stages in more detail to have a better understanding of how the Earth has changed. So there's different names that we give to different periods of time that have occurred within the Earth's history, and this is kind of a jargony way that geologists use to talk about, communicate about the different periods of time. And so there's kind of these nested categories that are more and more specific, and the broadest categories are called eons. There are 3 or maybe 4 eons, depending on who you talk to: the Hadean, Archean, Proterozoic, and Phanerozoic eons. And those are really long periods of time that occurred over, nearly billion years or something in that category. Then the most recent eon, the Phanerozoic eon, is broken into eras known as the Paleozoic, Mesozoic, and Cenozoic era. And then those eras are broken down into periods, and then periods can be further broken down into epochs. So there's these specific names, again, that people would know, things like Paleozoic or Cretaceous or Holocene, and these are names that if you use them, geologists would know what period of time that you're referring to. And so instead of having to use numbers to talk about when something occurred, they instead often just use these names to refer to the age of a particular geologic formation or a period of time in which something was occurring. And when we start to think about geologic time, it's kind of difficult for us to wrap our mind around just how long the Earth has been around. So we've already talked about the fact that the Earth has been around for about 4.6 billion years. Remember, GA stands for billion years, or Giga Annum. And again, we can break that time down into eons, eras, periods, and epochs. But here is an image of a way to kind of conceptualize that time, where it shows how much time occurred before a lot of the really modern things that we think of as not being modern at all, but as being kind of old historic things. So it's showing us in this particular diagram of this person's arm that, for instance, the Hadean Eon occurs near the shoulder, the Archean Eon takes up most of the upper arm above the elbow, the Proterozoic Eon takes up most of the distance from one's elbow almost through one's hand all the way towards one's fingers, and then it's only in the fingers that we get into the Phanerozoic Eon, which is where, again, a lot of the things that you've probably heard about have occurred. So the colonization of the Earth by land plants, things like dinosaurs, first primates, and of course all of human history are confined to kind of the very end of geologic time. So I think this is an image that gives us a little bit of perspective of how much occurred before we showed up. Okay, so we want to start from the beginning and talk about the Hadean Eon first. So the Hadean Eon refers to the period of time from the beginning of Earth's history to the end of the early late bombardment, we'll call that, about 3.8 billion years ago. And we already have talked about certain things that occurred during the Hadean Eon, such as gravitational differentiation. We talked about the fact that the Earth was very hot, it was liquid, kind of in a molten stage in its early infancy, and so because of that fluidity of material, gravity was allowed to pull the heavy materials down to the core of the Earth, and then the lighter elements were left in a concentrated way on the surface of the Earth, which gave us these different compositional layers of the planet. So we've discussed that before. We also know that there would have probably been a lot of volcanic activity, a lot of kind of bubbling up of material on the surface of the Earth at this time, and generally the Earth would have been hotter than today. So by about 4.4 billion years in the past, the surface would have been cool enough for some rocks to be formed, so there would have still been a lot of molten material, but we do have some minerals that we have dated back to this age. So 4.4 billion years is a long time that some specific minerals that we found in sandstone beds in Australia have been consistently existing since that time. So these particular minerals have never melted and reformed. So there must have been at least some pockets on the Earth that have gotten cool enough starting at that point to form these minerals and then remained cool enough throughout that over 4 billion year history. However, we also know that a lot of the minerals that may have formed early on in the Earth's history and other rocks that may have formed early on in the Earth's history have not been maintained throughout time, but they have been remelted, recycled, and destroyed. And one of the processes that really accelerated a fast rate of turnover of materials and rocks early on in the Earth's history was something that was called the heavy meteorite bombardment. And so because a lot of material in the solar system was still being pulled together by these gravitational forces that we talked about at the beginning of the semester, there was still a lot of loose material that was slamming into the Earth and kind of coming in, and the Earth was still kind of clearing its orbital path of debris. And so we do still experience meteorites hitting the Earth today, but not nearly at the rate that we would have in the past. And the high energy that would have been associated with all these materials slamming into the surface of the ancient Earth would have been, enough energy to destroy a lot of minerals that were starting to form. So the Hadean Eon is kind of marked from the beginning of the Earth's history until when this heavy meteorite bombardment stops, which we date to about 3.8 billion years ago. So, of course, we don't have any photographs of what the Earth looked like at that point, but this is kind of an artist's image of what the surface of the Earth might have looked like if it was covered with mostly molten material, some solid chunks kind of bubbling up on the surface, floating around in this molten, kind of molten material, lava streaming down the sides of some of these molten chunks, and then a lot of these meteorites or meteors streaming in towards the Earth. And then the chunks, if they make it down to the ground, are called meteorites. Here's an image of the earliest mineral that we have been able to identify on the planet. So I mentioned we have some zircon crystals that are found in sandstone beds in Australia that date back 4.4 billion years. So these are called the Jack Hills zircon. And you can see again that they date to very early on in the Earth's history. Another thing that we can see on the timeline on the bottom of this slide is that the formation of the moon would have occurred during the Hadean Eon as well. And we talked about the formation of the moon as likely being created when a planetoid slammed into the Earth, and then all the debris from the smashing of that, as well as the smashing of some of the Earth's crust, kind of coalesced around a new body that was orbiting the Earth, and that would have also occurred very on in the Earth's history during this kind of meteorite bombardment stage. But generally, one thing to note is that as geologists learn more and more about the Earth's history, and we improve our techniques to understand what was going on in the distant past, we're finding earlier and earlier evidence of minerals, and then also fossils that represent life. And so this is causing us to think that probably the conditions on the Earth's surface were perhaps more hospitable a little bit early on than people might have thought and discussed a decade or two ago. So it certainly was hot. It certainly was hotter than the Earth today, less hospitable than the Earth today in many ways, but maybe not quite as extremely hot for as long as we had originally guessed. Okay, so as the Hadean Eon ends, the next eon, the Archean Eon, begins. So that would be at about 3.8 billion years ago. And if we are thinking about the history of the Earth as a 24-hour clock, that would represent the time at about 4 a.m., so probably before most of you woke up this morning. And the Archean Eon would have been known for having high rates of hotspot volcanism, so there still would be a lot of heat in the Earth's mantle, causing convection, bubbling up onto the surface, and lots of different kinds of volcanic activity. But at this time, compared to the earlier Hadean Eon, we would start to have the formation of what are known as protocontinents. So these are not as big or substantial as the continents that we have today, but they would be big blocks of more felsic material that was being created as, lava was bubbling up onto the surface, leaving some of the heavier minerals behind and concentrating some of the lighter material up on the surface. We would have had these big felsic blocks of material, and as they cooled down and they grew in size, they would form again these kind of early continents. And so by the end of this eon, by about 2.5 billion years ago, most geologists estimate that about 80% of the continental crust that exists today was already formed. And so, again, earlier on in the class, when we talked about some of the difference between rocks in the ocean and rocks on the continents, we said on average the rocks on the continents are really quite old. And this is an illustration of that, the fact that for the last 2.5 billion years, 80% of the material that makes up the continents has been consistent and has not been recycled, but has been floating around and existing for a really long period of time. So that kind of sets the stage for what was going on in the Archean Eon. But some of the most interesting things that were going on in the Archean Eon is that this is when most biologists and paleontologists think that the first life forms evolved. So there is some debate about actually when the first life forms evolved, because it's sometimes difficult for us to be able to interpret exactly what fossils of the past represent the earliest life forms and what just represent things that look sort of like potential life forms. So the oldest undisputed fossils date back to 3.5 billion years ago, and that would be about 7:30 a.m. On our 24-hour clock. And these fossils are called stromatolites, and they're basically these big structures that are created by bacterial colonies, and the structures are kind of fossilized secretions that the bacteria would make. I kind of think of it like snot, where they kind of ooze material out around the areas where the bacteria were living, and then the bacteria would move into the next layer closer out towards the surface, and then move out closer towards the surface, kind of like corals do today. But anyway, many of these structures are fossilized in the ocean, and so you can see some of these things today. The picture in the middle is a picture of Shark Bay in Australia. And most geologists believe that these were created around hydrothermal vents in the ocean. So we talked about hydrothermal vents earlier on, these areas where hot water is kind of streaming up through the cracks in the rock from superheated magma underneath the surface. And this heat energy and also kind of the concentration of minerals around these things were allowing organisms to start to capture and transform energy to create life. So anyway, these early bacteria or cyanobacteria that we find still today in these kinds of environments are thought to be the oldest kind of organisms, with some caveats that we might have some that are even older. So it wasn't till later on, much later, 2.7 billion years ago, that we started to evolve photosynthetic organisms, and we'll talk more about those later. So I'll just show this one example of the fact that we are still debating this as scientists find more and more information about the past. It causes us to question the concepts and theories that we had about the original early life forms. So this is a study that came out 2 years ago that found all these kind of hollow tubes in these Canadian rocks that date back to almost 4.3 billion years. So that would be into the Hadean Eon rather than the Archean Eon. And some scientists think that these might represent fossils, perhaps kind of mineralized remains or fossilized remains of little bacterial filaments. So perhaps that is what they are, or perhaps they're things that just look like kind of similar to bacterial filaments, but actually represent mineralogical structures that aren't bacterial at all. So this is the kind of thing that people are debating about, and of course there's a lot more detail to the kinds of discussions and comparisons that they're making, but this is the way that new ideas are challenged and are created as people discover things, present them, debate them, and then over time decide, kind of as a scientific community, if it seems like the new hypothesis that people have put forward about an earlier time for life's formation might be possible or not. Okay, so the Archean Eon is a time of the formation of the early protocontinents and the formation of many early life forms, and maybe there's even some that dated from before that, but that's very much up for debate. But that brings us to the Proterozoic Eon, which starts 2.5 billion years ago and brings us up to 542 million years ago. And so on our geologic clock, 2.5 billion years ago would be about 11 a.m., so almost halfway through our 24-hour day. And the name Proterozoic actually means first life, and so at the time when geologists were naming these periods of time, they thought that the first life forms had evolved during this eon. We now know that certainly they at least evolved during the Archean Eon, and as we mentioned, perhaps even evolved earlier than that. So the name is kind of a misnomer, but it stuck around because people are familiar with it, and so it's still the name that we use to refer to this period of time. So during this period of time, there continued to be an expansion of continental material, continued to form slowly, and kind of by the middle Proterozoic, about 1.5 billion years ago, much of the modern structure of today's cratons had been formed. So cratons are a name for these big old basement rocks that make up the basement or the foundation of many of the continents that we have on the earth today. So cratons that you might be familiar with are things like the Canadian Shield. You might have heard of that before. This kind of big orange area that is shown, up in the Great Lakes region and up into Canada. And then some of these older other pink rocks that surround those orange rocks. Those are kind of the makeup of the cratons of the earth that exist today. So in North America, the oldest basement rocks are kind of underlying kind of Midwest and northeastern region, and then a lot of the western material in North America is quite a bit younger. So that wouldn't have been created by this point, but those older basement rocks would have already been created. You can also see big parts of Brazil, Africa, Eastern Europe, Central Asia, a lot of Australia, Greenland. These blocks had also already been formed and have been consistently existing, dating back to this period of time. So one of the most interesting things that was going on during the Proterozoic was a transformation of the Earth's atmosphere. And it was during this period of time that we started to have a buildup of oxygen in the atmosphere to create the kind of modern oxygen-rich atmosphere that we have today. And this period of time would correspond to about 2:45 p.m. On our 24-hour clock. And one of the pieces of evidence that we have for this transformation are these interesting geologic structures that are called banded iron formations. And I have a picture of a banded iron formation here on the bottom right, and you can see that there's these bands of really red and lighter rock, and you might already be familiar with the fact that when we see red in rocks and soils, that's an indication of oxidized iron. So there's iron that's bonding with oxygen that's building up in those layers, and then they're kind of layered in, alternating with rocks that don't have as much of that oxygenated iron. And so this, again, kind of represents this transition of the atmosphere that occurred about 1.8 billion years ago. And the idea of what happened to create these bands is that there was a buildup of certain kinds of cyanobacteria, blue-green algae in the ocean, and these organisms were actually creating oxygen in the air because they were starting to complete photosynthesis. Photosynthesis uses carbon dioxide and produces oxygen, and so these organisms would create this buildup of oxygen in the air. As the oxygen built up, it would start to react with surface materials and turn them red. And then the populations of these organisms would get so big, so fast that they would end up crashing, and there would be big die-offs of these organisms. And as they died off, then there would be a lower amount of oxygen being produced in the atmosphere. That would create these bands that weren't looking as red, and then as the populations of these organisms built back up, they would increase the amount of oxygen until over time the populations of these organisms kind of became more stable, and their contributions of oxygen to the atmosphere became more consistent after this period of time. But we have many of these banded iron formation structures all around the Earth dating to the same period that again represents this transitional period of the Earth's atmosphere from a low oxygen atmosphere to a atmosphere today that's about 21% oxygen. So this is a really important transition because oxygen is so important to the modern incarnations that we have of life. So the original organisms that formed, that we're looking at when we consider those really early fossils, used sulfur, and they split things like hydrogen sulfide to create energy to fuel their cells. And that process is much less efficient than using oxygen to be able to fuel your metabolic processes. So aerobic organisms are organisms that use oxygen. So that's like us and like most of the other organisms that live on the planet today. And again, once organisms were able to make this transition to using oxygen, they were able to be much, much more efficient than their anaerobic ancestors. So from about 1 billion years ago to about 4.542 million years ago, there was a huge transition in the complexity of life forms and the presence of multicellular organisms on the planet. And that kind of continued pattern of increase of complexity, punctuated with some mass extinction events, has continued to this day. And most biologists attribute that transformation to the fact that organisms, after the buildup of oxygen in the atmosphere, were able to transition to this more efficient process. So a few more things to mention about this Proterozoic Eon is that there were several past supercontinents before the most recent Pangea that we've already talked about. So there was one supercontinent that was called Rodinia that occurred about 700 million years ago. And this is an image on the right that's showing the different kind of pieces of today's modern continents, how they would have been different, and then how they might have fit together to form this past supercontinent. So on our 24-hour clock, that would have existed at about 8:30 p.m. And then Pannotia is another past supercontinent that occurred later on, about 570 million years ago, and that would have corresponded to a period of time about 9:15 p.m. So it's important to understand that these blocks of continents that were created early on have been moving around for a long time in the Earth's history. And so Pangea is one example of a supercontinent, but there certainly were other examples in the past. And also, we mentioned that we expect to see other potential supercontinents form from the building blocks of the Earth's continents in the future. So the very end of the Proterozoic Eon is marked by the creation of what's called the snowball Earth. So the snowball Earth was a time of rapid cooling in the Earth's history, where even the tropics were covered by glaciers. So all of the oceans would have been completely frozen over, and the Earth would have essentially looked like a giant snowball, which is how it got its name. So here's kind of a diagram at the bottom of the slide showing this transition into the expansion of this snowball Earth. And then eventually the Earth kind of came out of this snowball Earth period. And the theory as to why that occurred was that some volcanic activity that was being fueled by, processes below the Earth's surface continued to occur. And as that volcanic activity continued to occur, it caused a buildup of enough greenhouse gases in the atmosphere above the snow that the greenhouse gases were capturing enough heat from the sun that the heat was able to melt all the snow and kind of release the Earth from the grip of this snowy environment. And so many of the organisms that had existed on the Earth before the snowball Earth, you can imagine, found this environment to be very harsh, and there was a large extinctions associated with this period of time. And so as the Earth kind of transitioned out of the snowball Earth phase, it basically had almost like a blank slate where there was lots of new kind of uninhabited growing environments without a lot of competition in which new organisms could start to evolve. And so next time we'll discuss the fact that there was a huge explosion of new kinds of life forms that occurred at the end of the snowball Earth. And this end of the snowball Earth period would have occurred at about 9:20 p.m. on our 24-hour clock. All right, so we're going to stop there for today, and then next time we'll talk about the Phanerozoic Eon and the most recent part of the Earth's history.